So what lessons did we learn with this event? And what prompted the atmosphere to become primed for sustaining not only what we can call an outbreak of tornadoes, but the most historic and prolific day in South Florida. Obviously, we're not talking about the entire state of Florida. We're talking specifically the area of Lake Okeechobee and Southward. Obviously, Milton was the prime driver in terms of having those perfect ingredients. But let's look at the science behind this tornado outbreak, and we're going to bring our Science and Operations Officer, Donal Harrigan. Donal, thank you for being with us again.
Hey Tony, thanks for having me, and that was a fantastic recap of the event. It's really remarkable, and our forecasters did a great job during the day. It was a long day of many warnings and hard work, and we'll talk a little bit about why it happened. Now, the Storm Prediction Center has done some research over the years on tropical cyclone tornadoes and talked about some of those ingredients that make it likely that we'll have a lot of tornadoes and that some of them can be strong. So we do have ways to discern in advance what kind of day we're going to have, but a lot of stuff has to line up just right for that to happen. So we're going to talk about the things, and we're going to talk about it in the context of Helene and Milton, because Helene happened just a little bit before Milton did and didn't have near as many tornadoes in the South Florida area. So one of the ingredients we look for is that upper level support. We need to get the atmosphere rising. We need moisture in the atmosphere too, but the rising component of it has to do with this upper level jet stream. If you're on the southern part of the jet stream where the winds are starting to increase as you get close to it, you have diverging air and it's pulling air upward from the ground. So we have that lift and it's spread down all over South Florida. In addition to that, storm strength is important. So this would be the strength of Milton. When Milton or any hurricane gets strong enough, it penetrates up into the mid-levels of the atmosphere, which is what we're looking at here. So we see that signal as well. With the wind field, this is down more in the lower levels. We want a symmetric, large wind field, lots of turning in the winds, lots of increase in wind speed as it gets towards us, and influence well out away from the center of the storm as well. And then the storm size is important for that reason. We want it to spread out from the center because the center of the storm, if you see the hurricane, the eye is pretty continuous. It's rain bands, and we want for a storm to be able to produce a tornado, it kind of needs to live out on its own and have a little space to breathe, and we'll talk about that when we look at the radar imagery. So we had a lot of that in place for Helene also. This is for Helene. The main difference for Helene is that upper level jet stream was a little bit further to the north and to the west. It was still strong, but South Florida wasn't in the prime location for that upper level support to sustain those storms throughout the day. Everything else lined up just fine. It was a big storm. It had a big wind field. We had 60, 70 mile an hour winds with it. The other ingredient is dry air. Now, dry air, it can be counterintuitive because we talk about how dry air kills hurricanes, right? We want to see some dry air on the backside of this system as it approaches land. We saw that for Milton and Helene both. And what that allows it to do is wrap around into the storm. And so on those leading bands, some of that dry air can interact with the storms themselves and produce stronger downdrafts. Those downdrafts are part of what initiates the tornado and also keeps it going, like some of the long track tornadoes that we did see during this event. All right, so let's take a look on satellite at what that dry air looks like. So for Milton, all those reds, that's really dry air, but even when you get into the storm here, the blues and the greens, that means it's not deep layer dry air. So we have maybe just some lower moisture, so some dry air is starting to get in. And then with Milton over here on the more traditional visible imagery and infrared imagery, you can see some clearing out ahead, especially earlier in the day. Those are indications as well that dry air is getting in. And the other thing I wanted to point out was right here at the start of the loop, you can see this little burst of showers and thunderstorms moving off of Milton. Sometimes that produces like a little area of low pressure in the atmosphere that can help also enhance storm development later in the day. And watch, that's exactly what we saw. This is where the EF3 in Palm Beach County started. It was directly related to that little piece of energy moving off the storm. If we look at Helene, again, dry air all the way around the back, wrapping into the storm. But the difference here, a little too much dry air. If we look over South Florida, look how much clearing there is out ahead of the storm. Helene's track was a little bit further west and to the north, and so the core of that moisture was removed from us. I think there was just a little too much dry air to really promote storm growth as as Helene moved through. So we'll go back to focusing on Milton. One of the things on the smaller scale that we need if we want to see tornadoes develop is some sort of a boundary. And a boundary is really just like a slope in the atmosphere. So we need to get that rising motion. And so we have this area for rising motion where we have these red lines close together. That represents the temperature. And so we have wind bringing moist, warm air up. We also had clouds and rain to the north of Milton, which helped make that air cooler, so that tightened that boundary a little bit more. So we had that source for lift. That's good. Count that as the first check. The next one, we need instability, because the lift, or that little ramp, is like the speed bump. Once it hits it, what's it going to do? Is it going to go back down, or is it going to continue to go up? And the more instability you have, that means we're just going to shoot off of that speed bump, and we're going to have rising motion on the storm scale. The next is wind shear, and there's two components to it. This is the magnitude of the wind shear. So how strong are the winds, and how strong do they change, or how much do they change with height? Do they increase? That helps with storm organization. The other aspect of the wind is how is the direction changing with height? These are pretty complicated charts. If you're a weather enthusiast, you might recognize them as the skew T and the hodograph. But we'll try to break it down in simple terms here. The main thing we're looking at is how's the wind changing with height. So you can see the wind barbs here turning as you go up in the atmosphere. That results in a hodograph that looks curved like this. And you want a curved hodograph to see tornado development. And the area under that curve, the more area you have, the better chance you have of seeing a tornado. And you can see right before the tornado in Palm Beach County, this was the environment that we had, a sharp curve in the lower levels of the atmosphere and a lot of room under there, meaning we had a lot of storm relative helicity. With Helene, the morning started out just like that. We had turning winds with height, we had the curvature in the hodograph there, but right before all the storms started to develop, look at this, it's like a straight line. So all the winds were pretty much out of the south all the way up through the atmosphere, and that doesn't necessarily preclude a storm from becoming tornadic, but it will probably keep it from being that widespread day of strong tornadoes. Let's take a look at the radar loop. Again, we'll cover some of what T-Ray, that's what we call him here, Tony talked about earlier. As the day evolved, early in the morning we were able to see a tornado develop near Homestead area, and then some what we call discrete development, where the storms are kind of breathing on their own. They're removed from all that more focused forcing. They're riding that little slope up. And so we got some tornadoes developing on those, and then with that main band that came through with Milton, there was a little bit more forcing, some stronger winds, and we were able to generate those 2 EF3 tornadoes. So a very impressive day with multiple rounds of tornadoes covering a large area of South Florida. So what does it look like when we're sitting on radar and we're deciding whether we're going to issue a tornado warning? This is from the Miami radar, which is down near the zoo. This was looking all the way up at Palm Beach County. Which speaks to how impressive these storms were. You can make out some really good details and be confident that there was a tornado, even though it's relatively far away from the radar. So there's our reflectivity. This is what you typically see when you look at an app or on the television. That's where the rain is. And where the rain is, we also want to see some rotation. And so that's what we're seeing here. Red goes away from the radar. Green goes towards the radar. We're seeing that broad area of rotation called the mesocyclone. And then we also have the tornado, which is when you get those high values really close together. It's rotating really fast, it's smaller, that's the tornado. Further, since the advent of dual pole imagery, we can also tell a little bit how things are moving in the cloud itself. For example, this field over here, we won't get too much into it, but when you get the lower values lining up with the rotation, it's saying that something's tumbling around, something's rolling around. It doesn't know exactly what it is, but it's rolling. And then over here, this determines whether we have meteorological or biological things out there, if you will. And so where you have the red and the pink, that means it's rain. And here it means it's something else. So this is how we know there's debris. There's something that's not rain tumbling around where we have the rotation. And this is where the tornado was the EF3 in Palm Beach County. You can see that signature is highlighted there, very strong. Rotation still looks good. I mentioned we were a little ways away from the radar there. We also have radars up and down the East Coast called terminal Doppler radars. They're located near airports, and they're meant to detect wind shear for planes taking off and landing, but we use them to get a look throughout our whole forecast area at the low levels. So it's very important. It gives us confirmation that there is something not just happening aloft, but down low. And we were able to see this tornado right here Red is away from the radar. Green is into the radar, so we had that rotation. It was very close together. And a traditional looking debris ball on the reflectivity from the Palm Beach radar as well. Here's where it is, in this area where it's quiet, where there's not much there, and the tornado was just a couple streets away from actually hitting the radar. And again, this is where it was when we had the EF3 in Palm Beach County. So in summary, what do we have? We have favorable positioning of the upper level jet stream. We got a large wind field. We have a large and strong storm, okay? And then we have some dry air on the backside that will wrap in. Then you get down to the storm scale and you have the instability, you have the wind shear, you have the forcing and the turning of the winds. So everything lined up for it, Tony, and you know, hopefully we don't see it again, but it's something that we know to look out for, and we hopefully are able to communicate that message to you through watches and social media.